Okay, excellent. So this is going to be a transition from starting from the visual dialogue. What I want to do is I want to talk to you about three things, but I'm going to talk about the first one in detail, and if I can't get into the other stuff based on your questions, I'm happy to skip over some things and talk to you after the talk. So the thing that I really want to get into is this project of cooperative visual dialogue agents, which is taking a step from visual dialogue supervised learning towards RL. I want to tell you a little bit about experiments that we've done on emergence of language, of grounding in dialogue agents talking to themselves, and some recent work which was just a really fun project to work on, which is on making two dialogue agents negotiate with each other on a negotiation task. So that was a fun thing to do. Okay, so the first one. So as you know, this is something that we're working on, that we worked on. So Devi got into this thing that, the task for visual dialogue is you're given an image, you're given a history of human dialogue, question answers, you're given a question, a follow-up question, and you're supposed to answer it. But why is this task, and is this a good task? There's a few different problems with this setup, right? The first problem is that there's no goal. Why are we talking? Why is the answering agent supposed to answer questions? Presumably the goal defined is just to help someone or to provide information, to help them do something downstream, but that isn't explicitly clear. The way we're training these agents is to mimic humans. The other thing is that the agent answering the questions or it's not in control. The agent is artificially injected into a conversation that was being taken between two humans, asked to provide an answer, and then at the next round, you just basically forget what the agent said because the dialogue history is again the human dialogue history, right? It doesn't matter what you said, I'm going to again inject you at the next round into somebody else's conversation. So the agent doesn't get to see its errors during training. And obviously the third thing is that, which is also related, is that the agent never learns that there are equivalent utterances that mean the same thing for the downstream task, because there are many ways of answering the same question, but the agent doesn't really know that because it keeps getting penalized on log likelihood of the human response that the human said at that instance. Okay, so here's a way to fix some of these issues. It's not going to fix everything, but here's an image guessing game between two agents. So meet two agents. There's a Q bot and there's an A bot. The Q bot is blindfolded. It asks questions. The A bot is an answering bot. It answers questions about images. It sees an image. What we're going to do is these two are going to play a game where the answering bot will start off by, and this is going to seem very similar to the data set, the answering bot will start off by captioning this image, right? Two zebras are walking around their pen at a zoo. That's all that the question bot hears. The question bot does not see the image. The question bot asks the question, any people in the shot, right? This is not human dialogue. This is generated question by the agent. Are there any people in the shot? The answering agent answers that question. No, there aren't. Any other animals? No, just zebras. Are they facing each other? They aren't. This conversation goes on for, let's say, 10 rounds. And at the end, the questioning bot is provided with a pool of images and has to pick which image were we talking about, right? We just had a conversation. You asked me some questions. I provided you some answers. Which image do you think the other side is providing these answers to? Okay, that's the setup of the game. And based on the accuracy of prediction of this image, they both get a reward. They're a perfectly cooperative team, and they both will do well on how well they did on questions and answers based on this thing. So this actually solves some of the problems that I was talking about. Now there's a goal. Why are we talking? Because later on, one of us is going to have to pick this image out. That's why we're talking. And we get to see the equivalence of the responses. And how good is my response? It's good if it helps you do something downstream. Does that make sense? Okay. So I'll sort of get into a little bit of details here. Yes?
I'm curious, was the data collected with this task in mind, or it was...
The data was not collected. So the idea of this game happened after the data was collected, but it was incidental that this is extremely like the task that we gave to humans. Humans were never actually asked to do this secondary thing that actually picked this image out, but they were asked to, when the data was collected, to build a mental model so that later on you can pick this image out of a lineup. It never really struck us that after you do that, you can actually train these things to do that. Yeah. Okay, so you guys have gone over an entire summer school on RL, so what I'll try to do is at least just ground my notation so that you can relate it to other talks that you may have seen. So the agents, there are two agents, but because it's perfectly cooperative, you can think of this as one single meta agent with two subcomponents. We're going to learn both their policies. The environment is a pool of images and the target that only one agent sees. There's going to be an action space. So the action space for the questioner bot is a sequence of symbols. There's a vocabulary of, let's say, English words or some tokens, and the questioner has an action space, which is pick a sequence of symbols that you can send to the other side. And the answerer has a similar action space. The questioner has an additional action space, which is regress to the features of the image that we're talking about. And that's how we're going to do this image guessing. We're not actually going to pick from a lineup. We're going to make a continuous prediction. It's a vector in some 4,000 dimensional space. It's what would be the embedding of this image from some CNN, the last layer of a CNN. So we're trying to make this continuous so that we can write down continuous losses and differentiate through. Does that make sense? So the action space is not discrete about the image picking, it's actually continuous. And because there is private information, the state spaces are actually different. For the questioner bot, the state space is caption followed by the sequence of conversations that we've had. And for the answer bot, it's image that it sees and the caption and everything else, the entire conversation. Right? So that's the state space at any particular time. You have an action. We're going to write down a policy. These two are going to operate under a policy that generates a question given the past history of conversation, and the actioner and the answerer A-bot also has a policy that generates an answer. Right? So it's going to be a policy over a sequence of symbols. Does that make sense? And we'll get into these policy networks, what exactly they are and how they're trained. But before we get to that, we're going to define a reward function. The reward function is going to be at every round, you had some conversation that had already taken place. You decide to take an action, which is you asked a question, the other side responded, you made a guess. Did that help or not? So this is loss function. Y is your prediction of the image features. L is some L2 distance, some smooth loss function. How close are you to the actual ground truth features? And did you improve, did you decrease that by asking this question or not? So that's the reward. Yes?
During the game when this way you set it up was at the end you see the image?
Yeah. So the short answer is because RL doesn't work. The long at the end of an RL summer school, maybe not the right statement to make, because because it's hard. If you have really long delayed rewards, if you think about what's happening, your action space is really large. You have a sequence of potentially unbounded list of tokens that you can have. You have to emit a stop token. That's your question. The other side has to produce an answer. If the reward is at the end of 10 rounds, the signal is pretty weak by the time you do this. So that's why there's these extra reward signals after every dialogue utterance. And what that also lets you do is it lets you define incremental improvement. Did this question help your prediction based on what you already knew? And that really helps get the right thing. But you're absolutely right, that's the right way to do it. We're working on it. We will, ideally that's what you'd like. To give the ability to stop asking questions and say, I'm ready to make a prediction, and then have the reward. Yes? Is there a question? There's a sigh. Okay, so the reward, yes?
I have a question. So does this preclude, I guess, a certain set of questions? It seems like pairs of questions that might be really helpful to ask might not be helpful in this framework.
Yeah, this is greedy at every round of the dialogue, right? So what you're asking is, can I initially take a hit only to later on have a benefit in my thing? Yeah, that wouldn't emerge from this sort of a reward structure. But what you have to realize is just learning to ask a sequence of symbols is hard enough. Thinking 2 times ahead, we can get to that in a later project. Yes?
Well, I had another question, but just on that note, like if you're not discounting, then it should still be able to do this kind of long-term planning, right? Because it really, I mean.
Yeah, if you're not discounting, then the rewards are additive, so the intermediate stuff just cancels out. Yeah, thank you.
So the question I had, and I think maybe you are getting to it, but is there any way that the symbols are actually incentivized to relate to natural language in the way that we use it?
Yeah, so what we're going to do is we're going to pre-train on the supervised data that we already collected. So we are first going to show human dialogue history, show what the human asked next and what answer the human gave. That's the pre-training, and we're going to do RL fine-tuning. Yes. And we're going to make sure that they don't drift away from human language by every so often looping through the supervised learning patches. Any other questions? Okay. So that's the reward. I've defined now an agent, an environment, state, what actions we can take, what the reward function is. The only thing remaining is what is the policy that we're operating under. Here's what the policy network looks like. It's going to have two major components. There's a questioning agent that has its own policy network that asks questions. There's an answering agent that has its own policy network that produces answers. The only communication and sharing that happens between them is through discrete tokens. They share no other parameters, no word embeddings, nothing. And one of the reasons for doing that is to prevent leakage. There is private information that is present on the answer bot. If you share any parameters, then you can basically communicate the FC7 vectors of that image. Here's what that full architecture looks like. I'll walk you through a couple of these things. They're fairly intuitive at an individual level. There's a question decoder, which is essentially an LSTM that at a word-by-word level decodes a question. Based on the past history, any people in the shot. And there's a stop token. You ask that question. The other side has access to an image that it's processing through a CNN. It's listening to the incoming question through an LSTM as well. So encodes the question through the last hidden vector representation of this question. It's actually doing a hierarchical embedding, which is work out of McGill, which is on how do you encode dialogue over sequences. It's a two-level encoding where you're encoding every caption and question answer as a fact that you know about the image. So two zebras are walking around their pen at the zoo. This is a sequence that you embed once through an RNN. You embed all other question answer pairs like that. And then in a hierarchical manner, these F vectors, which are embeddings, you're embedding them through a second layer LSTM as well. That's your state encoding. There's, of course, an answer decoder. There's a similar history encoder on the questioner side. And ultimately, there's basically a regression engine, which is a fully connected layer that takes everything, an encoding of all history that you know, and regresses to the FC7 features, so 4,000 dimensional features. And ultimately, that's being fed into a reward. All of these parameters on the questioner side, on the answerer side, everything is being learned end-to-end from that reward. Yes?
So, do you think that if you collected the data with this task, based on this task specifically, your RL problem would be easier and you might not require this kind of step-by-step reward function? So what I'm saying is you're just training to imitation learning maximum likelihood on the data might get you closer to the policy for which you could just train. Curious about that.
So that would require us giving humans that secondary task, exactly. Pick an image, and if they got it wrong, then this dialogue is that gives us a quality on this dialogue, that even though you see this as supervised data, it doesn't lead to a great reward.
What I'm imagining is that you would actually get different kinds of questions also, right? So that you would incentivize them in some way.
Yeah, maybe. But I think actually seeing the kinds of strategies that you hope to execute later on and examples of that would definitely help. What I'm really hoping is that the hope here is that you can do supervised learning to get into the space of asking questions and answering questions. And then RL is what gets you to discover strategies that help you on your reward. Yeah. Okay. So this isn't particularly too complicated an RL algorithm. We just went with something really simple and standard. So everything that you've learned in this summer school, that's all ripe for being applied to this task. It's just vanilla reinforce, where you write down that what you care about is an expectation over your policies of the reward function, and you're going to use just a simple log likelihood trick to swap things out and say, I'm going to write the expectation of this reward with respect to expectation of the gradients with respect to the policy times the reward. And this is a fairly intuitive interpretation. If the reward is positive, it means the question that you just asked helped your prediction over the past round. So increase the gradient, so increase the probability of that dialogue exchange. If the question that you just asked hurt, then decrease the probability. That's just what that thing is doing. Okay, here's a really simple, here's a Turing test. There's an image, there's a caption. The caption was written by a human. The image is, of course, the image. One of these two is chat between two humans. So human questioner, human answerer. The other one is chat between these RL agents, the RL questioner and the RL answerer. Which one do you think it is? The top is the human questioner, human answerer, or the bottom is the human questioner, human answerer? Bottom is human. The ellipses indicate that the string was long and I clipped it, but other than that, that's the actual generated thing with no pre-processing. The top is human and the bottom are the RL agents. And you can, there's one way that I knew you could tell. What is the man wearing? Black t-shirt and jeans. The jeans isn't visible. It's actually just making that part up. But the good thing is that it's nice to see that these things, these are some of the better examples, but they're getting up there.
So they're not native English speaker humans?
I mean, Mechanical Turk. Yeah, so humans being Mechanical Turk, they are restricted to the US, but still. Yeah. Here's another interesting thing that happens between the SL agents, so the human mimicking agents and the RL fine-tuned agents. This is a common problem that they fall into. The supervised learning agents, how old is the man? Pretty quickly they'll fall into repetitions. What color are his shoes? Black. What color are his shoes? Black. What color are his shoes? Black. They're asking the same questions over and over again. This has been observed even in non-visual dialogue or just dialogue in general. The RL agents, even when they are uncertain, they will convey that uncertainty and write out something longer after that because they are trying to optimize downstream reward. I can't tell is a high likelihood sequence, but doesn't help you in your reward. That's why they sort of are trying to say something after that. Here's quantitative evaluation. We can actually measure on the x-axis are rounds of dialogue. 0 is starting from the caption. 1 is the first question asked, and so on. The red is, so the blue is called SL pre-trained because that's the supervised learning agent. That's what the RL starts from. That's what we do RL fine-tuning. And so the improvements that you're seeing there on the y-axis are, they're shown a list of 10,000 images in there, and based on their regressed features, you sort them and you look at where they place the actual image. And so the y-axis is showing percentiles. So percentile improvement of 3% is 3% of 10,000 images. So there's a lot of actual ranks that you're pushing this over. Yes?
What do you mean by supervised learning pre-training? Are you training to just output the questions that
Yes.
to the data set?
What the human asked. So you show them human dialogue, show them what the human asked as the next question. That's the supervised for the questioner, the answerer, the same thing. And what is the supervision for the image? Well, we know what image this dialogue was conducted on, so try to regress to its features.
There is a supervised method that might give you the same performance as your RL algorithm, which is just doing the one step ahead, like asking a question and then computing the cross entropy of that answer. Oh, sorry, computing the distance from your embedding of the image, right? That's your loss, right? So you could just do that at one step ahead, and that could be a supervised learning baseline.
Yeah, except I can't differentiate through, well, at least when we did this, you couldn't. Now with maybe Gumball Softmax, you can, but you can't actually differentiate through the question asking part because that's discrete. So you can't, yeah.
So but you could just try to train, now we
Yeah.
can approximate that. And train.
Yeah.
Okay.
That's something that we've thought about since that paper came out, that sequence of continuous relaxations through Gumball Softmax, yeah. Okay. Any other questions?
A question.
Yes.
What is baseline performance for this? Like maybe how many images are they guessing from?
So it's 10,000 images that they're guessing from. The way to think about this is that 0 is starting from the caption. So that's caption-based retrieval. So you embed the caption through an LSTM and try to regress to image features, and with full supervision, try to regress to the image features and do nearest neighbors in that 10,000 pool. So that's getting you to this point, right? The reason why these two are different is because even the captioner is fine-tuned through RL. So getting to 89% on that means that 10% of 10,000, so you're looking at 1,000 images. That's the confusion that you can't do better than, because there are so many images that are semantically similar that can be described by similar captions. So that's sort of a baseline to compare to. So dialogue over that is helping. Yes. Sorry.
After two questions, actually it's not possible to increase the score anymore. So in some sense, is it just looking for key discriminative questions and put apart that part?
Yeah. So we're not really sure if it's, so yes, the answerer definitely changes because the answerer stops saying things like I can't tell, I don't know. It actually starts expressing uncertainty but saying something more, like what color is the skateboard? It is hard to tell, but I think it's black. Like there is no way to say that. Like is it night or day? It is daytime. Is he wearing knee pads? No knee pads. And so it actually says more things, and that actually helps the questioner build this mental model. We've looked at question types that it's asking, and we're not really, like, we haven't nailed down if the question types are particularly different. I think one thing that for me was interesting was that supervised learning with more dialogue interactions actually starts hurting. So initially it helps, and then you're basically off, because if the supervised learning agent says something wrong because it is inaccurate, the questioner is going to treat that as the right answer because he's never seen mistakes during training, and going to start follow down a conversation thread that actually starts hurting. That at least doesn't happen in the RL agents.
I was wondering what's the computational complexity of the action space. So, are you picking questions as in sentences?
No, you're generating word by word. Yeah.
Word by word.
So
So if you were to pick two only, because you have a language model and so on, so the space is constrained.
But the language.
Could you come up with a different optimization algorithm? Because reinforce here is being used as an optimization algorithm, but fundamentally it's not an RL problem.
If we did
Not
delayed.
a sequential decision-making problem.
No, if we had delayed rewards, then it would definitely be an RL problem. Right now, it's at the cusp of, the only reason we use our reinforce in this is because we had a discrete action space, right? We had discrete variables that we were trying to optimize. But if we had delayed rewards, that you ask 10 questions and then there's a reward, then it would be totally in the realm of RL, right? That you have to make a sequence of decisions and you get the reward which is downstream, and you don't get to see the reward after every action, for example. So you have to plan ahead in advance.
I tend to think it's more like what would make it an RL problem is if you had a model.
Well, I mean, the model is sitting in the head of the humans. There is a model. We just don't have access to it. Like, there is a way to, like...
Yeah, in a sense, you're simulating the
Yeah.
world, yes, with the agents. But you only get one single reward at the end. So
Sure.
It's one shot.
We can take this offline. Yes?
So you said that the RL agent is still doing better when there's no dialogue. Like, they're trying to optimize the same loss, right?
At 0, the RL is doing better because it's actually even fine. So at round 0, it's caption. The caption is generated by the answerer, and we are fine-tuning even the answerer all the way back to round 0, so it generates better captions. So they don't always start from ground truth captions. So in supervised pre-training, they see ground truth captions, but the RL agent has the ability to generate its own caption at round 0, right? So it's a better captioning algorithm because at round 0, it's generating its own caption. Does that make sense?
I must be like kind of confused about the whole setup because I thought the goal is to actually just output the image, basically.
That's for the questioner. The questioner is outputting the questioner is regressing to the image.
Okay.
So the goal for so here's the action space. The goal for the answerer is just to answer. This is the only action space for the answerer. Just answer this question. The questioner is going to regress to the image features. But they're both, because this is being treated as one agent, it's perfectly cooperative. They're both their policies are being learned. Yeah. Yes?
Can you go back on the reward definition, please?
Yeah.
If I'm not mistaken, in the reward actually depends of some hidden states that is not in the states, because there is a ground truth, so it should break the Markov assumptions. So my question is, did you observe in the long run that the algorithms start to diverge or not? Because we lose any guarantee of convergence because of that.
Yeah, I mean, so one thing that we're doing is we're having to in order to not drift away from human language, after some batches of reinforce, you're also having to do batches of supervised. Like so all of those guarantees are out anyway, right? Where it's not entirely clear what your objective function is there that you're optimizing. But yeah, you're right. The reward actually does depend on the true image which the questioner does not have access to. Yeah, that's a good point. Okay. So that was that. Oh, I want to say that some of this is also concurrent work from Aaron and his collaborators on the guess what work. So I won't be able to get to all three, but I want to tell you about the next one because I think I can get done pretty quickly. It's related to this one. So this is a more toy setup. It's the same setup of two agents talking, but instead of real images, this is going to be a completely synthetic world. Images in this world have only three attributes. They're of different shapes, triangle, square, circle, star, different colors, and different styles. Those are the only three attributes, and perception is perfect. The answering side can exactly see those three attributes as one-hot vectors, let's say, right? And the goal is the answering side is provided exactly an instance represented as a tuple of those three, so purple, square, filled. And the questioning side is given a task. Inquire about the color and the shape of the thing that the answerer is looking at, right? It's a very specific task. Order matters. You're always asked about two of the three things that exist in the world, and the order matters. Are you being asked about color or shape, or shape or color? Okay? So there are 6 possible tasks. 3 choose 2 times 2. They always engage in 2 rounds of dialogue. The vocabulary is completely ungrounded. The questioner side has some alphabet. The answer side uses some numbers. The vocabulary of the 2 sides does not have any predefined meanings or any word embeddings, right? So this is what a dialogue looks like: Y2, Z3, and you have to make a prediction. Purple square. That's what the other side was seeing. You have to, based on that prediction, you get a reward +1, -1. If you get exactly that pair right, you get +1. If you get that pair wrong, you get -1. And learn. And there's no supervised pre-training, there's no English, there's no sequence of symbols. That's the task setup, and you backprop the whole way through with reinforce. And this is a delayed reward setting, so you don't get supervision after every round. Does that make sense? Okay, if you do this, grounding of symbols emerges automatically from that task definition. So X basically gets grounded. So here are dialogues that basically emerge that these 2 agents partake in. X3, Z4, it is always the case that X means that the agent is asking about the color, and Z means that the agent is asking about style. 3 means that when it's for X, it means the color green. 4 means that it's a solid style. And so we sort of have these, symbols get grounded into shapes and into attributes on the questioning side, and symbols get grounded into their values on the answering side. And for us, this was pretty cool that you can do this where there's color shape gets YZ and shape color gets YZ, and the questioner basically swaps it out later. But there's this sort of there's this translation chart that we can look at post hoc of these dialogues and figure out what they were talking about. The interesting thing for us is this does not automatically happen in every case. If you give them really large vocabularies, so for example, the world in this case has only 4 colors, 4 shapes, 4 styles, so there's 4 times 4 times 4, 64 possible things. If you give them a vocabulary of size larger than 64, then grounding does not emerge in this compositional manner. What the answerer will do is basically take every tuple, encode it as a symbol, and just send that, and dialogue even isn't necessary. And that was interesting for us to see that, if you want natural looking compositional language to emerge, you have to do these fairly intricate things like have a small vocabulary with respect to the space of possible experiences that you can have to describe. And interestingly, the answerer's memory has to be taken away. The answerer cannot remember what it asked on the previous round, because if it does, then they coordinate on these set partitioning type things. And basically what that does is that your answer 2 has to mean the same thing on round 2 as the same as round 1. And that's what leads to consistent grounding. And again, there's been a really nice flurry of papers on topics of multi-agent dialogue and the emergence of language in these settings from a number of different groups, and I encourage you to check them out. This is a really nice, exciting area. This last one I won't have time to get into, but I'll just tell you what, at a high level what this is. We trained 2 agents to split a set of items by talking about it in natural language. It's a negotiation task where if you walk away from a deal, you get 0 reward, so you have incentive to cooperate. And it leads to fairly interesting sort of, I'll show you an example. It leads to fairly interesting things where there are items that you want to split. They have some value to you, they have some value to someone else, and you engage in this dialogue. I'd like the ball and the hats. The other side says, I need the hats, and so on. And ultimately, you agree on a deal. And once you train these agents, they can actually, we propose a technique where you can think ahead with the consequence of your actions, basically dialogue rollouts. If I say something, what's going to happen? And it leads to fairly interesting sort of chatbots that you can negotiate with. And if you do RL fine-tuning on this, they get really aggressive. They do not take a bad deal. And Mike in particular, who's the lead author of this, said it was frustrating to negotiate with these agents because they have infinite patience. They just will keep negotiating, but humans tend to walk away. So I'll stop there and I can take questions. Thanks.